Okay, so let's see. Yeah, so in the last class, the thing that we tried to do was to define a notion of the directional derivative of a vector field. Okay, and this is different from the directional derivative that we defined for a scalar field last time. So now imagine that over this entire manifold, over an entire manifold M, there's a vector field W. Okay, so at let's say the point P, there's a vector WP. At a point Q, there's a vector WQ. And now these points P and Q, okay, you can think of them again. Remember that if you think about small displacement vectors, so you can think about a vector V which displaces you. So this vector V lives in the tangent space at P, but it displaces you in some direction along the manifold. Okay, and so in that direction, if you have a small displacement by an amount epsilon, okay, in the direction towards another point Q, you'd roughly like to define the derivative of this vector field along the v direction. Okay, so this is the derivative of the vector field W along the v direction. Okay, along the v direction, and this is defined at a point P. Okay, so at a point P, you're defining what this derivative is. And intuitively, the rough idea that we would have for how to define such a thing is you take the vector WQ, that is the vector W, the vector field W has a value at the point Q. So find what that vector is. Find the vector at the point P, take the difference between them, and divide by epsilon, where epsilon is this displacement. Okay, intuitively, this is the simplest thing that you could think of. However, this is not really a straightforward thing to do, okay, because what we saw last time is that the vectors V belong, this vector WP, okay, belongs to the tangent space at the point P. The vector WQ belongs to the tangent space at the point Q. And a priori, there is no obvious correspondence between these two vector spaces. Okay, even their basis vectors are different. Okay, for example, if I look at the basis vectors at the point P, then the basis vectors at the point P are in a coordinate basis, let's say, are partial x mu. Okay, but these are evaluated at the point P. Okay, or if you like, at x of P. Okay. So these are basis vectors in TPM. Okay, and partial x mu evaluated at xq. These are basis vectors in TQM. Okay, so a priori, there is no obvious relationship between the one basis vector, let's say even the x0 basis vector here and the x0 basis vector here. Okay, they're evaluated at different points. So even if you think of them as these derivative operators are acting differently, okay, because it's a derivative at a different point. So there's no obvious way in which you can relate, okay, these two things. I mean, you can make a choice, but there's no defined choice for you in terms of how to relate these two, okay, or in general, how to relate any vector WP, which can be expressed as a linear combination of these basis vectors, and any vector WQ, which can be expressed as a linear combination of these vectors. There's no obvious way to relate them. Okay, so what we would like to do is define a way to relate the vectors WP to something inside the tangent space at Q. Okay, so we'd like to somehow transport WP to the point Q. Okay, and when we get it at the point Q, we'll call this vector W prime P. Okay, so this is the transported version of WP, and we'll say it's parallelly transported, okay, to the point W, to the point Q, and now, now it has it's some W prime, okay, at the point. Okay, let me just denote it as W prime P. It's the parallelly transported vector which was actually at P, but now it's in the tangent space at Q. Okay, so P prime also belongs to TQM. So what we want is some way to relate the vector that we started with, which was in the tangent space at P, to this new parallelly transported vector, okay, which is in the tangent space at Q. Okay, so this was the basic picture that we had last time. So this was the point P, this is the point Q, this is WP, this is WQ. We want to compare them with each other. But to compare them, we have to move this vector WP and we have to find an analogous vector. Okay, sorry, I didn't note it as W prime Q. So this vector here is W prime Q. Okay, it's in the tangent space of Q. Okay, so this W prime Q is WP parallelly transported, but we have to define a notion of what we mean by parallel transport when we move it to the point W prime Q. Okay. Okay. So now, then it makes sense. Okay. Once you transport this vector from here to here, then it makes sense to subtract take the difference between WQ and WQ prime. Okay, so this allows us to define a difference vector, and this difference vector divided by epsilon, which is this displacement, that then gives you the directional derivative along V, okay, of the vector field W evaluated at the point P. Okay, so this is all evaluated at the point P. So in other words, if we take the difference between these two vectors, okay, what we're doing is this is WQ, this is the transported, okay, parallelly transported WP. Okay, and we take the difference between the two, which is this vector. Okay, and this vector divided by epsilon, which is that infinitesimal displacement. Okay, that is basically what we define in the limit epsilon goes to 0. That is what we define as this derivative operator on the vector field W at the point P. Okay, is this clear?
Sir, I have a doubt.
Yeah.
Sir, instead of transporting P to the point Q, can't we transport Q vector to the P vector? Because when we are subtracting WQ and from WQ prime, what you would get is a vector which belongs to TPQ, right? Sorry, the tangent space of point Q.
Right. Okay. Yes, you can define it that way. Okay, so roughly speaking, the difference between these two things, it doesn't really matter, okay, because these points are epsilon close to each other. It's like saying, let me define the derivative at x, okay, let me define f prime at x as this, or should I define it as this? Okay, it doesn't really matter because the points, once you calculate the derivative, the point x plus epsilon and the point x are effectively the same point. Okay, so this is like saying this is like evaluating something at x plus epsilon. Okay, this is like evaluating something at x. Okay, so it doesn't really matter because at the end, once you calculate this difference, I could have defined this as maybe this is the derivative at the point Q. Okay, I could call this maybe the derivative at the point Q rather than at the point P. But the point is P and Q, and as you correctly pointed out, because now the way I've done this would now be a vector at TQM. Okay, and now the thing is, now if P and Q are infinitesimally close together, once I've defined the derivative, then I don't worry about the difference between P and Q anymore. Okay, one after you've taken the limit, then you can say that this is the derivative either at the point P or the point Q. Those points are infinitesimally close together, so it doesn't really matter after I've taken this limit. Okay, I don't need to distinguish between them anymore. Does that make sense?
Yes, sir.
Okay, so thanks. That is a good subtle point that's important because this indeed, as you pointed out, this difference vector, the way we've defined it, belongs to TQM. Okay. Okay, so what we need, okay, basically the thing that's missing in this definition is the prescription. Okay, what is the prescription by which we will take a vector from here and transport it to some vector here? Okay, a manifold by itself doesn't give you that information about how to transport a vector. This tangent space and this tangent space have nothing to do with each other a priori, okay, except for the fact that there's a smoothness of the vector field. There's some notion of smoothness that you can define. Okay, these vector spaces are sort of unrelated to each other. Okay, so these are different vector spaces. So how do we define the notion of parallel transport? Okay, so we need this prescription, okay, for how to move a vector from WP to WQ prime. So on any manifold, okay, so this is, we're not even talking about metric spaces now, okay, we're just talking about parallel transport on a manifold. So there's no special metric that we're defining, okay, so there's no specific notion of distance, only displacements. On a manifold, we need additional information, okay, or we need some kind of set of rules, okay, and the set of rules which defines parallel transport at every point. So at every point in the manifold, you need some rules which will tell you how to transport vectors to infinitesimally nearby points. Okay, so such a rule is given by something called a connection. Okay, so this is the important idea that we'll try to discuss today. What is a connection? Okay, essentially you think of it as a rule, and this rule is at every point P, it tells you how to transport a vector to some adjacent nearby point Q. Okay, so so we'll derive these rules, and these rules are for any manifold. Okay. Okay, but you have to prescribe the rules. The rules don't come with the manifold. So just like when you go from a manifold to a metric space, you're prescribing a specific tensor. Okay. When you add a connection, when you prescribe such a rule for parallel transport, this is an extra feature that you're adding to a manifold. Okay. However, as we'll see, if your manifold also has a metric, okay, and this we'll see not today, but maybe in the next class. If your manifold has a metric, okay, then the set of rules, the preferred set of rules or the connection actually becomes unique. Okay, there's a natural unique connection or a unique set of rules which you can use for parallel transport. Okay, and our familiar rules of, let's say, in Euclidean space, how we parallelly transport a vector, and we think of this as parallel to this, that really relies on our common sense intuition. This common sense intuition of parallel transport really relies on this unique choice of the rules for parallel transport. Okay, so this parallelly transporting a vector in 2D or 3D Euclidean space, that relies on a specific metric. Okay, the fact, and we'll see later how this rule follows from this metric. Okay. But in general, if there's no metric on the manifold, okay, you need to prescribe those rules. Okay, the rules are not part of the manifold itself. Okay, so these additional rules need to be supplied to describe how to parallelly transport a vector, and therefore how to take directional derivatives of vectors, of vector fields. Okay. So let me define now the idea of a connection. So first what we'll do is we'll kind of do a heuristic derivation, okay, of what the connection is and what it means. And later we'll try to do a slightly more rigorous mathematical definition. Okay, so this basic idea of the connection, or this rule for how you parallelly transport vectors. So you can understand why it's called a connection, right? It's a connection between 2 points, which tells you how to transport a vector from here to here. That's what we mean by a connection. Okay, so the manifold does not tell you what connection to use, but here are some properties of the rules that we'll demand. Okay, for this rule about transporting this vector from here to here, let's demand some rules. Okay, so we want to transport a vector W along a direction V. Okay, and this will result in a vector W prime. I'll suppress the fact that this is at P and this is at Q. Okay, so sorry, so WP, yeah, so let me just write WP and W prime Q. So WP in components in some coordinate system, we would write it like this: WP mu partial x mu. Okay, at P. In WQ prime, we would write like this. This is W prime Q mu, okay, partial x mu evaluated at Q. Okay, and we want to transport, okay, this vector from the point P to the point Q, and this is along some direction, okay, where we define a vector V, which in components is V mu partial x mu. Okay, so in coordinates, let's say the point P, and we'll assume that this is an infinitesimal displacement. Okay, so P, we want to P going to Q. So P is, let's say, has coordinates x, and Q has coordinates x plus delta x. Okay, where we can write this as x mu and x mu plus delta x mu. Okay. Now our first rule, okay, that we'll demand, and this seems like quite a reasonable rule, is in this coordinate system, okay, in a particular coordinate system that we're choosing, we'll take w prime q mu, okay, this component of this vector, and this component of this vector, okay, and we'll say that the difference, okay, should be proportional to this small displacement, okay, of coordinates. Okay, that seems like a very reasonable thing. In the limit that this displacement goes to 0, okay, you should not have any change, right, in the vector. Okay, that's a reasonable rule to have. Okay, and we're also assuming that this displacement is small, so the difference between these two vectors is only showing up at first order, okay, in delta x. Okay, doesn't higher orders you can ignore. Okay, the limit delta x goes to 0. So we're only interested in the displacement being so the change in the vector is, or vector components rather, the change in the vector components is delta x mu. Okay, note that this difference now is not a difference between vectors in different tangent spaces. Rather, we're talking about a vector in the tangent space TQM. We're talking about the coordinates of this vector in this tangent space in a particular coordinate basis. Okay, in a particular coordinate basis. And we're talking about the same thing at the point P. We're talking about the components of this vector WP mu using the same coordinate basis. Okay, the same coordinate basis, partial x mu. Okay, and in that coordinate basis, we're just saying that the difference between these components, these coefficients, okay, that difference is proportional to delta x mu. Okay, the second rule that we demand, okay, is that if we take a vector at q, okay, so this is, so sorry, if we have two vectors w1 plus w2, and w1 and w2 are two vectors at p, and we parallelly transport both of them, okay, or we parallelly transport the sum of them, okay, then the parallel transport of the sum of them, which we'll denote as w1, so if I take the sum of them, maybe it's this vector, okay, and if I parallelly transport the sum of them, that is some vector w1 plus w2 prime. Okay, what we want is, again, in this particular coordinate system, if we parallelly transport w1 plus w2 to w1 plus w2 prime, which has a component mu, okay, this should be equal to the parallel transport of w1, the parallel transport of w2. Let me take w1 prime, this vector, and w2 prime, this vector. Let me add these two vectors together, okay, and let me take the muth component of that. Okay, this is different from taking the sum of the two vectors first and then parallelly transporting. So basically, we're saying that taking the sum of vectors and parallelly transporting is the same as parallelly transporting, okay, and then taking the sum. All right, so so that's what this means in components again. Okay, in components, we're relating the components like this. Okay.
Sir, here w1 plus w2 is a vector at p, right?
This is w1 plus w2 prime. I put a prime on the whole thing. So w1 plus w2 is a vector here at p, as you're saying, but w1 plus w2 prime is that vector w1 plus w2 parallelly transported to q.
And on the right hand side, w1 prime and w2 prime are also vectors at q.
Sorry, yes, these are vectors at q. That was a mistake. Yes, these are vectors at q. Yes, indeed.
Yes.
Yeah. Okay, good. So this is basically about linearity of parallel transport, or basically it's parallel transport is commutes with the operation of addition of vectors. Okay, that's quite a reasonable rule to impose. So we'll only impose these two rules, okay, on for how to parallelly transport. All right, that is the change in the vector components. The change in the vector components in a coordinate basis is proportional to the displacement, okay, in coordinates. And the second rule is that your parallel transport is sort of commutes. Sorry, maybe this is not, it's not the right statement of linearity. Okay, parallel transport commutes with the operation of addition of vectors. Okay, so it doesn't matter whether I add them first and then parallelly transport, or I transport and then add. Okay, you'll get the same result. Okay, so these rules, okay, actually define a correspondence between vectors in different vector spaces. Okay, in a particular coordinate basis, where Q, P belong to the same coordinate patch. Okay, so the vectors Q and P, sorry, the points P and Q we're assuming belong to the same coordinate patch. And we can easily see that these rules can be satisfied if we take this assumption. Okay, so we take W prime Q mu, okay, to be equal to WP mu. So this is the components of the vector at the point Q. Okay, these are the components of the vector at the point P. Okay, and as we said, the difference between them, we want it to be proportional to some delta x. Okay, so it's proportional to the size of the displacement delta x, which we write as delta x nu. Okay, we choose some particular direction nu, and the other thing that we require, okay, for the fact that it doesn't the second rule is satisfied, okay, is that it's also proportional to the components of W. Okay, it's proportional to the components of W, so it's proportional to W lambda P. Okay, so it's some other component of W. And now what we need to do is for every W lambda and every X nu, since these are arbitrary, okay, we need to choose a set of coefficients. Okay, so we're choosing so this is an equation for a particular muth component of the vector. Okay, so let me draw this to make it clear. So this is a point P, okay, and this is a point Q. So let's imagine to get from P to Q. So I'm just drawing it in a coordinate dependent way. So I could go like this. Okay, so this is displacement delta x1. Okay, this is the displacement delta x2, and this is the net displacement. Okay, it's delta x1 in one direction and delta x2 in the other direction. And now what we want is the vector which was here, okay, which had so this I can break it into components. Okay, and we're looking at, this is one component and this is another component. Okay, so this is W mu P. Okay, so this is W2P and this component is W1P. And now we parallelly transport this vector so that it's over here. Okay, and again we can break it into components. Okay, and this we call this W prime to Q, and this component is W prime 1Q. Okay, in the horizontal direction. And now we want a rule which relates the new component, okay, that is the W, let's say the W prime 2Q component, to the original W 2P. Okay, this is the second component of W at the point P. So we're saying that these two are the same, but except for this fact that you can also have some extra change, okay, in this vector, and that extra change is proportional to okay, so it's proportional to either delta x1 or it's proportional to delta x2. It can have some amount of change in either of these directions. And so that's what I mean by taking different nus and so there's an implicit summation over nu and lambda here. So I've taken a summation over nu. Okay, so this is delta x1 and delta x2. So it depends on how much I displace in this direction and how much I displace in this direction, but it's linear in those displacements. Okay, the second thing is now we need to include things like this change in this second component can be proportional to W1. Okay, but it can also be proportional. This change can also be proportional to W2. Okay, and so now what we need in general, sorry. Okay, now what we need in general is a coefficient, and this displacement can also be proportional to W1 and can also be proportional to W2. Okay, and so you have four terms now. Okay, assuming this is a 2D manifold. And now I need coefficients. Okay, so I can choose an arbitrary coefficient here, an arbitrary coefficient here, an arbitrary coefficient here, an arbitrary coefficient here. These coefficients, for example, this coefficient is denoted as gamma 2, okay, to remind me that I am talking about the second component of this vector, okay, and 1, 1, okay, to remind me that this is the coefficient of W1, okay, which was this thing, okay. Again, this is at P, okay, and this is gamma, sorry, I hope this is visible. Is it too small on your screens? Just let me know if it's too small. It's visible, okay. And this is gamma, again, the upper index 2 tells me that this is the second component of W prime Q2, okay, being related to WP2. And the lower indices would be 1 and 2. Okay, sorry, 2 and 2. Okay, because this is now the coefficient of this W2, WP2 and delta X2. Okay, similarly, I'll get some other numbers here. So I'll get minus gamma 2, and then I'll get 1, 2. And I'll get mine over here. I get minus gamma 2, 2, 2. Okay. Did I make a mistake? Sorry, this is 2, 1. Okay, so each of these constants is different. Okay, and a priori, okay, you don't know what to choose for these constants. Okay, now you might think the most straightforward thing is, why don't we choose all of them to be 0? Okay, and that is a choice that you can make. Okay, but it's not a choice that the manifold necessarily gives you. Okay, so you can, in principle, any of these choices, any choices of these gammas, okay, is a valid choice. Okay, under our rules. Okay, as we'll see, there is a unique choice once you impose a metric. Okay, and once you impose this kind of metric in a Cartesian basis, okay, we'll see that the gammas indeed do work out to be 0 in that basis. Okay, but it's not necessary that on an arbitrary manifold that these gammas should be 0. Okay, and in fact you can choose them to be whatever you like. Okay, on an arbitrary manifold. Okay, you can prescribe these rules. All right. And in general, once you have a metric, the prescription for what these gammas are gets fixed. Okay, these coefficients get fixed once you have a metric. We'll see that there's a unique choice of these coefficients once you know the metric. That choice may not be 0. Okay, for general metrics. Okay, so for example, in, let's say, curvilinear coordinates or polar coordinates, these coefficients will be non-zero in general. Okay, so even in a on a flat metric, but if you're in coordinates which are let's say spherical coordinates or something like that, these coefficients will be non-zero. Okay, so we'll do some examples later maybe to understand this. Okay, so this is the general rule. Okay, so what we have now is, let me just rewrite the general rule here. Okay, this is the general rule. So the new components of the vector W are related to the old components, but they can also have additional corrections. And these corrections are proportional to the small displacement. And they're also proportional to different components of the original vector itself. Okay, and there are some coefficients, and these coefficients, basically the rule for how to parallelly transport is the rule for prescribing what these coefficients are. Okay, you tell me these coefficients at every point on the manifold, and I can tell you how to transport the vectors. Okay, that's what we mean by specifying the rules. Okay, so if you know gamma, this is equivalent to specifying the rules for parallel transport.
Sir?
Yeah.
I'm sort of confused about the notion of parallel transport. How, I mean, you said that for P and Q we are taking different tangent planes. Then parallel to what, basically?
Oh, so this is a notion of okay, so this notion of transport is such that we're trying to keep this vector. Okay, so this is at the moment parallel doesn't mean parallel in the sense of Euclidean geometry. Okay, parallel is just a term. As we'll see in the specific case of, we'll see what it mean, why this is called parallel transport later. Roughly speaking, the idea will be, let's say on a plane, once we impose a metric and a particular that metric gives us a unique choice of these coefficients, we'll see that parallel transport will really translate to moving a vector such that even here you can think of the tangent space at every point as being different, but it'll come to our usual notion of if I have Cartesian coordinates, right? Parallel transport will mean really just keeping the vector parallel to itself as I move it to a different point. Okay. On a manifold, so now the thing is, if you have polar coordinates, okay, so let's say this is x and y. If you have the same flat space, okay, so this is same Euclidean space, but I'm just going to switch my coordinate system. So in Euclidean space with polar coordinates, okay, so I'm just in 2D space. Let me just erase this. So now I'll define a point by its r value and a theta value. Okay, so now my coordinates are like this. So now, first of all, let me define what my vectors are. So my vectors will be partial r and partial theta. Okay, partial r, as we've discussed, these vectors also generate infinitesimal displacements in the r direction. So partial r, you can think of, even though we've written it as a derivative operator, you can think of it as a vector which is pointing in the radial direction. Okay, partial theta is like a vector which you can think of as pointing in this direction. Okay, and this is at some point P. All right, and now what we take is some other point Q. Okay, so we take some other point Q. So let me just imagine that displacement is, let's say, in the theta direction. Okay, so Q is displaced relative to the point P only by displacement in theta, not in R. Okay, so it has the same value of R, and this is now a theta plus d theta. Okay, now again you can define the vector space at Q, and the vector space would be partial theta and partial r. Okay, now you can see that in your Cartesian basis, this basis, okay, that is this basis here, is clearly rotated with respect to this original basis, right? These two bases are rotated with respect to each other. Okay, if I increase the angle, it'll be even more obvious, right? If I increase the angle like this, okay, so for example, something like this, this is so this is my r theta, and this is r theta prime. Okay, then this is partial r, and this is partial theta. Okay, but this is evaluated at point Q, and this here, this is partial r, and this is partial theta, but this is these derivatives are evaluated at the point P. So in the compared to the Cartesian basis, you can see that this, okay, these two vector spaces are rotated with respect to each other, okay, compared to your standard Cartesian vectors. Okay, so now what you want to do is, suppose you have a vector, let's draw this WP. This is a vector that lives at this point P, and you want to parallelly transport it to this point here. Okay, we'll see that the notion of parallel transport will be such that, let's say, parallel transport would lead to something like this, WQ prime, right? So that in Euclidean space, you can see that this is parallel to this. Okay, but if you break this WQ prime into components, okay, in this new basis, okay, you'll clearly see that this doesn't have the same components that the original vector had. Okay, whereas in Cartesian coordinates, if I have this basis here, this basis here, this vector, they'll all have the same components. Okay, in the new basis. Okay, here this vector will have different components from this vector. Okay, and so basically our rule is basically telling us how to relate the components of this vector in this new basis to the components of WP in the old basis, okay, which will involve some corrections. And you can understand what those corrections are. Okay, those corrections basically involve the fact that these are rotated, okay, and for small angles of rotation, that is if theta prime minus theta is small, then it should just be proportional to something like d theta, okay, which is the displacement from point P to point Q. Okay, and also it will be something like, since it's a rotation, okay, roughly speaking, you'll have things like W prime, let's say in the theta direction, okay, and W prime in the R direction. Okay, so I'm just going to write it as partial theta and partial R. Okay, this will be related to a linear combination of, so I'll just call it W prime R, W prime theta. This will be some linear combination of W prime R, sorry, WR and W theta. Okay, times some d theta. Okay, and W theta. Since it's a rotation, roughly speaking, it will look like this. Okay, which is an infinitesimal version of cos theta minus sine theta minus sine theta cos theta WR W theta. Okay, I'll give you some exercises to try to work out things like this. Okay. Okay, so this will be the rule, and you can see that this is kind of similar to the kind of expansion that we're doing, right? Where we're trying to work out what these coefficients are. In this case, the coefficients would be, let's say 1 or something like that. So you're expanding W prime and components, and it's some WR, plus it can in general have things like the displacement and components of the original vector that you started with. Okay, and then some coefficients here.
Sir?
Yeah.
Just maintaining the components, I mean, the rule being that just you maintain the components, WR and W theta, would also be a valid parallel transport as of whatever we have discussed right now, right?
In one coordinate patch, you can always choose gamma equal to 0 as a valid rule, right? But for example, you see that would not, I mean, that would give you a different rule, right? In polar coordinates, if I chose that rule, then what I would mean by parallel transport would be very different, right? Because what that would mean is that then the notion of parallel transport, since my axis, so let me. So you have to choose the gammas in some coordinate system. Okay, so you choose them in some coordinate system. Okay, but once you choose them in some coordinate system, then the relationship, if you transform to another set of coordinates, then the rules are fixed. You'll just have to transform the rules. Okay, so you fix them in one coordinate system. So suppose the rule was that in the polar coordinate system, in this r theta coordinate system, gamma was equal to 0. All the gammas are 0. Then the rule would look very different, because now what you're saying is that the components of the vector, okay, so this is the vector space partial r, this is the vector space partial theta, this is a vector w. Okay, and now this is, if this is a new point q, this is partial r and this is partial theta. And now if you're saying that the components of the vector are the same, okay, then what you're essentially doing is saying it has the same component along the partial r, which is this, and it has the same component along partial theta, which is this. Okay, so I put this component here, and these two together give me this. Okay, so now clearly this vector is not in the usual sense parallel to this vector. Okay, this vector is not parallel to this vector. All right, since so this rule, by choosing this rule, okay, you've defined a notion of parallel transport. Okay, and in fact this notion of parallel transport is basically saying I will rotate w, okay, this vector w, as I rotate my coordinate axis. Okay, that's essentially what the rule is that you're ascribing to parallel transport. That is a rule that you can choose. Okay, and that's a perfectly valid rule for a connection. Okay, mathematically this is still called parallel transport. Okay, although this is not the same as our usual notion of parallel transport. This is a rule for how to transport vectors from one point to another.
Yes, sir.
Okay. Okay, there's another property of the. Okay, maybe I'll get into the subtleties later. Okay, so any choice of these gammas in principle is a valid rule. Okay, and you have to specify the choices of gammas in some coordinate system. But once you specify in one coordinate system, the rules are fixed. Okay, what you physically mean by these rules gets fixed, and you can translate that rule to another coordinate system if you like. Okay. So what are these coefficients gammas? Okay, so the coefficients gamma are basically, so for each value of mu, nu, and lambda, okay, which is if you have a dimension n manifold, each mu, nu, and lambda each take values from 1 through n. Okay, mu goes from 1 through n, nu goes from 1 through n, lambda goes from 1 through n. Which means that you have to specify these numbers, these coefficients, n cubed coefficients have to be specified at every point P on the manifold. Okay. If you specify these numbers at every point P, or equivalent you specify n cube functions, let's say on the manifold, okay, again, these functions can be defined patchwise, okay, and they have to be smooth and so on. Then you have a connection, okay, so this is a rule, and this gammas are called connection coefficients, okay, they tell you a rule for parallel transport. This rule may or may not agree with your intuition of what parallel transport should be in Euclidean space, but it does define a rule, okay. So later we'll see that with a specific choice of metric, we get our intuitive rules for parallel transport. Okay. So specifying gamma on the full manifold, okay, is basically the same thing as specifying the rules for parallel transport. If we specify these coefficients gamma, we have the rules for parallel transport on the whole manifold. Okay. So that's why the specification of this connection, or the connection coefficients, that is equivalent to specifying how we are going to parallelly transport vectors. This is not a property of the manifold itself. It's some additional property that you need to impose on a manifold. Okay, you need to prescribe these connection coefficients. Okay, as we will see later. Okay, and there are many choices for a given manifold. There are many possible choices for what you can impose for this connection. For a manifold with a metric, there is one specific choice of a connection, okay, which is quite natural to use. Okay, again, you could use a different connection, but there is one specific choice of a connection which depends on the metric, which is quite natural to use. It's the choice that preserves the inner product of vectors. Okay, so we'll see that the choice which preserves the inner product of vectors, that is, if I have two vectors v and w, the notion of a dot product between them is only defined if I have a metric. And that dot product, if we want it to be preserved, the value of the dot product between these two vectors, if we want it to be preserved under parallel transport, then there's a unique connection which does this. Okay. So we'll try to find out what that unique connection is, maybe in the next class. Today we're going to talk about this in more generality. Okay. Manifolds, not necessarily with a metric, with general connections, which don't have to be what are called metric connections. Okay, there are arbitrary connections. There are many possible gammas. Out of these gammas, one special one gets picked once you have a metric on the space. Does that make sense?
Yes, sir.
Yes, sir. Would the converse also be true? So if we specify a gamma which satisfies our natural intuition of distance, it fixes a metric. Right?
That's a good question. Okay, so if I specify the gammas, does it uniquely specify the metric? I mean, in this natural way. I have to think about that. Okay, maybe we'll do it in the next class when we derive the specific metric, whether the formula is invertible. Okay, that is, can I go from the connection to the metric? From a general connection, can I get a metric associated with it?
Sir, about the natural way of defining a parallel transport, that works in flat space because you have, for example, a predefined underlying coordinate basis that is same for everything. So you can say that, oh, this is parallel to this. When you go to the curved space, you don't necessarily have that, right? Because you may not even. So how do you?
Okay, no. So that natural basis that you're talking about in flat space is a very specific basis in which the metric takes this form. So it actually has to do with the metric, not the fact that, so the flatness of space doesn't have to do with a particular basis. Okay, it has to do with the fact that, okay, in that one basis, the metric can be put in this form. But for example, I can go to polar coordinates, and as we've seen in polar coordinates, so for example, in 2D, right? So this is, let's say in your XY, this is your metric. But in polar coordinates, this is your metric. Okay, but they still describe exactly the same space. Okay, at least if I remove the origin, right? If I'm describing the patch without the origin, which is without the point r is equal to 0, these two metrics describe exactly the same thing. Right. So the fact that space is flat has nothing to do with the coordinates that you put on the space. We haven't described the notion of flatness formally yet, but it doesn't. It shouldn't have to do with the coordinates that you put on the space.
So in curved space, what would be your natural notion of a parallel transport?
It's the one which preserves the dot products, okay, between vectors. So we'll have to define a metric on a curved space. Okay, so curvature is defined again through the metric. Again, let's wait till we define the notion of curvature.
So then the question is answered, right? If you can't have a dot product without defining a metric, how can you define a connection in a natural way?
Yeah, exactly. So it's only when you have the metric that you can define the notion of dot product, and then the special connection is the one which preserves the dot product under parallel transport.
Okay, all right, thank you.
Okay. Okay, so now let's define, for example, the covariant derivative. Okay, so now we want to define the derivative of some vector field W. Okay, along the direction V. Okay, so this is what we mean by the symbol. And so we'll take V to be an infinite displacement vector. Okay, so something like delta x nu partial x nu. And for the moment, let's just pretend that these delta x nus are non-zero only in one specific direction. Okay, so there's no real summation over nu, only one value of nu. Okay, so no summation here. So we'll take only one value of nu. Okay, so let's say, for example, there's a displacement only in the x1 direction. Okay, so only that value of nu, okay, is what we're thinking about here. And so now the way we define this delta V of W, okay, is we take our vector field at the point Q, and we parallelly transport the vector which was at the point P, okay, and that gives us this in components, and we divide this by the displacement, which is delta x nu. Okay, and since there's only one direction, there's only one value of that displacement, which is delta x nu. Okay, and what we want to do is then take the limit of this delta x nu going to 0. All right, so this is it. Okay, so this is how we calculate the derivative. And so this is very simple to see now. We use our rule for what is the parallelly transported, what are the components of the parallelly transported vector. So that is WP mu. Okay, so I'll just leave this as WQ mu minus WP mu. Okay, divided by delta x nu. But now I have this plus, okay, plus gamma mu nu lambda. Okay, so we had defined these coefficients with an overall minus sign, I think. Yeah, we defined this with an overall minus sign here. Okay, and once you define it with those coefficients, then you get a plus sign here because you're subtracting off that parallelly transported vector. So you get plus gamma mu nu lambda, WP lambda at P. Okay, and then the delta x nu cancelled out. Okay, so there's delta x nu and delta x nu, so I can write it explicitly. Okay, there's a delta x nu, and then there's a divided by delta x nu. So now this whole thing I want to evaluate in the limit that delta x goes to 0. Okay, so in the limit delta x goes to 0, the first component, the first quantity that I've written here is nothing but partial w mu partial x nu. Okay, it's the change in the the muth component in some coordinate basis. Okay, it's the derivative of w, the muth component, with respect to the x nu coordinate. Okay, and then what I have here is very simple. It's just gamma mu nu lambda w lambda. Okay, that's what we have here. So now what this does is it defines for me delta VW, okay, and I'll say this delta V is corresponds to a displacement V which was in the direction nu, okay, because we only assume this is non-zero in some particular nu direction nu. So this defines the this derivative in the nu direction, and it gives me the muth component of that derivative. Okay, it gives me the muth component of that derivative. And the muth component of that derivative is just this. Partial W mu, partial X nu, plus connection coefficient times W lambda. Okay, and there's a summation over lambda over here. All right. So the way to read this is the muth component of the directional derivative of the vector field W. Okay, so there's a vector field W, and I parallelly transport the vector from here to here, again WQ prime. I take the difference between these two. I divide by epsilon, which is the displacement. Okay, and this is in the nuth direction. So the direction is in the nu direction. And now I take the difference vector divided by epsilon, and I evaluate that the muth component of that. Okay, the muth component of that is this right hand side. Okay, so it's the muth component of the directional derivative of the vector field W in the nu direction. Okay. Okay, in some coordinate basis evaluated at the point P. Okay, so this is the derivative, and we associate this derivative with the point P. Okay, any questions here? I'll pause.
Hello, sir.
Yeah.
So these gammas are evaluated at point P, right?
These gammas are, yes, so they are at point P in this rule. Yes. Again, since this again, there's a subtlety because I'm defining this after I've taken the limit. And so after I've taken the limit, it doesn't really matter whether I think of this as point P or point Q because they're infinitesimally close together. Okay, you have to be careful about the distinction here before you take the limit, but after you take the limit, the distinction doesn't matter anymore. That's higher order, and once you take an epsilon going to 0, it doesn't really matter. So yeah, that is another point, that these connection coefficients have to be smooth. Okay, that is, if I evaluate this at the point P and if I evaluate the next thing at the point Q, the difference between these should be small. Okay, and it should go to 0 in the limit that P and Q come infinitesimally close together. Okay, so it can't, this connections cannot be discontinuous numbers. It has to be somehow a continuous distribution of these connections over the entire space. Continuous and actually differentiable. Okay, any more questions?
Sir,
Yeah.
if we parallelly transport a vector from P to Q, then the gammas are evaluated at P before taking the limit. But if we start from Q and if we go from Q to P, then gammas should be evaluated at Q. But shouldn't then the gammas at Q be negative of gammas at P?
No, because delta X would be negative if you go from Q to P.
Oh, yes, sir. Yes, sir.
Yeah, delta X would be. Okay. So now let's more formally define this notion of this derivative. Okay. So this derivative is some operator, and what this operator does, now this operator can act at any point on the manifold, or in general it acts on all points on the manifold. You can think of it as acting at all points. So what it does is we define this chi of m to be the vector space. Okay, it's the sorry, chi of m is the set of smooth vector fields over the entire manifold. Okay, or another way of denoting it is it's, if I take tensor fields, it's the 1-0 tensor fields over the entire manifold. Okay, so these are smooth tensor fields or smooth vector fields over the entire manifold. So I take two smooth vector fields as input. Okay, what are these inputs? One is the direction along which I'm taking the derivatives. Okay, so v at every point gives me a direction on the manifold at in which I'm taking the derivative, and w is the vector field of which I am taking the derivative. And the result of this operation, okay, we're defining this operation such that the result of this operation is some new vector field, which I'll call okay, we won't give it a notation, but let's say we call it u. Okay, so this, we won't use this notation later, but this entire thing is some vector field. Okay, so these chi m are smooth vector fields. So if this delta satisfies certain properties, then it's called an affine connection. Okay, so it takes two vector fields as input and returns a third vector field. So it's, mathematicians called it an affine connection. Physicists called it a covariant derivative. Okay, so let's define this notion of what this derivative is. So the derivative, as I said, takes two vector fields x, y, and gives you some other vector field which will denote as delta x, y. Okay, and the properties of this derivative are such that, okay, if I take instead of y, I take y plus z. Okay, that is, I'm differentiating the sum of two vector fields y and z. Then I will get the sum of delta xy and the sum of delta xz. Okay, this is a vector field, this is a vector field. The addition of those two is another smooth vector field. Also, this makes sense. Okay, this is a nice property that you'd expect derivatives to satisfy. Then you'd also have a rule like this. Okay, so if I have delta x plus y z, okay, so now I'm differentiating along. So I have a vector x, I have a vector y, and I have some third vector z. So I take the derivative along the x plus y direction. Okay, this is the x plus y direction. I take the derivative of z along the x plus y direction. That should be the same as the derivative of z along the x direction plus the derivative of z along the y direction. Okay, this is another rule that we demand for this derivative. And a third rule that we demand is that if we and this is actually one of the most important properties of this defining this derivative, is that if we scale, okay, so now we have vector field x, we have a vector field y. Okay, this is of course only at a point. I will have different vectors at different points. So at this point, okay, if we scale x by some f, okay, which means then this f is a smooth function, which means at some other point this f could be different. Okay, this is f evaluated at the point q times x at the point q, and this is y at the point q. Okay, so this derivative along the fx direction rather than the x direction is simply f times delta xy. Okay, that is, the derivative doesn't act on f. F is just a scaling of this overall derivative. Okay, so f just becomes a scaling of the overall derivative. This is a very important rule, okay, which distinguishes this derivative from other kinds of notions of derivatives that you can have. Okay, in particular, the derivative doesn't act on x or fx. Okay, it's just linear with this any scaling of this vector x. Okay, so if I make this vector 2x or 3x at a particular point, I will just get twice or thrice that derivative. Okay, with respect to the original x. And this would be true everywhere in the manifold. Whatever I scale x by at any point on the manifold, okay, that coefficient would pop up here instead. Okay, and now the other rule is if I take delta x acting on fy, that is, if I scale y, the derivative acts on f and it acts on y. Okay, so how does it act on f? Well, it acts on f by how would you smoothly you think about two things. One, you think about the Leibniz rule. Okay, that is, I want a derivative, some notion of a derivative. When it acts on AB, there should be some kind of product rule. Okay, so it's like it acts on A, and then it acts on B. Okay, so the action on B, okay, which is Y here, would be it acts as a vector field derivative of Y. Okay, and this returns a vector field, and then I multiply by the scalar function f. The first term here is I pull out the y, but now I want this del x to act on f. Okay, and we define the notion of a directional derivative acting on f. The most simple thing to do is define it the way we had defined it before, which is these vectors are anyway operators. We define them as operators. So let's define it as that operator acting on smooth functions. So let's define it as x of f. Okay, so we want a derivative operator which satisfies these four properties. Okay, where these functions f belong to smooth functions on the manifold f of m, and xy are smooth vector fields on the manifold. Okay, so smooth scalar fields can be denoted as tensors of type 0, 0, and smooth vector fields are tensors of type 1, 0. Okay, so these spaces are the same, these spaces are the same. Okay, so now if we just look at these rules, okay, we'll be able to construct exactly the same notion of a derivative operator that we did heuristically, okay, in the beginning of this lecture. So we'll use a particular coordinate chart u phi, okay, and we'll define n cube functions, okay, on the manifold. We'll define these gamma, lambda, nu, mu, and we'll define them in such a way that that this notion, so that is, if we take grad v of x, we'll take x to be a particular basis vector, okay, and basis vector field. Okay, so this is defined at all points on the manifold, and similarly v is some partial x nu defined at all points on the manifold, and we'll define this derivative, and this derivative gives you a vector at all points on the manifold. Okay, and what we're saying is that this vector, okay, which we're writing as this, by definition is the derivative along the e nu direction of the vector field e mu. Okay, this is valid in a coordinate patch. Okay, this is only valid in some coordinate patch. We write this as some some connections, gamma, lambda, nu, mu, times e lambda. Since this should return a vector for you, I can expand it in a vector basis. Okay, and these are the basis coefficients. Okay, some gamma, lambda, nu, mu, and these vary at different points on the manifold. Okay, where these e mu's are just partial x mu. Okay, these are your original basis vectors. So yeah, okay. So the result of acting on any particular basis vector, okay, should just return for you some vector in the space. Okay, and this vector can be expanded in some basis again. Okay, it's the same basis e lambda. All we need is some basis coefficients. Okay, which is gamma, lambda, nu, mu. So if we specify these coefficients, okay, at every point on the manifold, we specified the action of this derivative. Okay, so just specifying these rules is not enough to specify the meaning of the derivative. There are many such derivatives for different choices of these basis coefficients which satisfy those rules. Okay. Okay, so now we'll be more general and say, okay, what is the rule if I take a general v, okay, and some vector w? Okay, then again I can expand v in that basis. I can expand w in that basis, and now we can take v nu derivative along the e nu direction. Okay, so this is coming from rule number. Okay, let me just check if you guys understand this. So when I say that I'm pulling out this v nu over here, okay, which rule am I using out of these four rules that I had?
Third rule.
Yeah, we're using the
It's actually both the second and the third rule, because then.
Yeah, very good. We're using both the second and the third rule. Okay, the second rule because this is a sum over basis vectors. That's a good point. Okay, there's a sum over basis vectors here. Okay, and these have arbitrary coefficients. So first you can think about doing this for each one. So now I'm pulling. So first I have a summation, and then instead of doing the gradient like this is equivalent to doing the gradient of first V0 E0 plus gradient of V1 E1, okay, and so on. And then what we're doing is we're pulling out these coefficients here, which is rule number 3. Okay, so we get V nu here, okay, and then the gradient of E nu acting on W mu E mu. Okay, so this uses rules 2 and 3. Okay, now the next step is that we're going to use our rule number 4, okay, which is our Leibniz rule. Okay, actually we'll use rule number 1 and 4 now, because there's a summation here. Okay, so this gradient will act on W and it will act on E mu. So I'll write it as E nu acting on W mu times these E mu. This is the product rule, right? This derivative first acts on the coefficients, then I can pull out the coefficients and it acts on the basis vectors. Okay, and now what you get is V nu, E nu acting on W nu. W mu is just a scalar function, okay, because these are just coefficients. So these are scalar functions on the manifold. So these are just E nu acting on them is just partial x nu acting on these coefficients W mu, okay, and this E mu remains. This second term over here is V nu, which I pulled out common, W mu, and now the action of gradient of E nu, I just call this derivative of E nu on E mu, that gives you your connections. Okay, it gives you gamma lambda mu nu E lambda. Okay, so now overall, finally, I can write an expression for what I mean by this gradient of V on W, or derivative of V along the V direction of W. Okay, I get in components, I get V nu times, I'll pull out this E mu common. Okay, and here you can see what I'm going to do. I'm going to change lambda. Lambda is a dummy index because I'm summing over lambda. And mu is also dummy index because I'm summing over mu. And what I will do is I'll change lambda to mu and I'll change mu to lambda. Okay, when I do that, this becomes E mu and I pull it out common. Okay, and the coefficient that I get is W lambda gamma mu lambda nu. Okay, so again, what you get is this gradient, this derivative of W along the V direction is this. Okay, this is a vector. Okay, the result is a vector. These are the vector coefficients in here, and these are the basis vectors. Okay, so this defines for me a vector. Okay, and the muth this is the muth component of the vector. Okay, so this del V on W is a vector, and this is the muth component of that vector. Okay, because this is the coefficient of the E mu basis vector. So the muth component of this basis vector is just this. It's V nu partial W mu partial x nu plus W lambda gamma mu lambda nu. Okay, again, to specify the meaning associated with this derivative operator, you need to specify what these connection coefficients are at all points in the manifold. Okay. Okay, so in short, we can write this like this. Okay, we'll write it as V nu times, we'll define this entire thing to be the derivative of W along the new direction, and we're trying to find the muth component of that derivative. Okay, this is the muth component of that derivative. So in other words, we're writing it like this: del nu W mu. Okay, you have to be a little careful here. We're not taking the derivative of the muth component. Okay, this is the derivative of W. The derivative of W is a vector. The muth component of that vector is this. Okay, this is the muth component of the vector, the derivative along the nuth direction. Okay, so it's partial W mu partial x nu plus W lambda gamma mu lambda nu. Okay, it's the muth component of the derivative when the derivative is taken along the direction nu. Okay, so intuitively, there's one direction mu and there's one direction nu. Okay, and I have a vector W. I have a vector W, I take the component of W in the mu direction, and this, sorry. I have a vector W, okay. I take the derivative of W in the new direction. So as I go in the new direction, I find out what is the change in W, okay, change being appropriately defined by, so I move in the new direction, I move to this point Q. Okay, so this is the point P, this is the point Q. I find out what is the change in the vector W. Okay, so I have some other vector W here because this is a vector field. So I have to parallelly transport this here, take the difference, divide by epsilon and so on. Okay, and then I get some new vector over here, and or let's say rather, it's a new vector over here, and I take the component of this vector along the mu direction. Okay, so this is the derivative, this is the derivative along the mu direction. That's what we mean by this quantity. Okay, so be very careful when you see the symbol delta nu W mu. Okay, this is not to be interpreted as this. You're not taking the derivative of the muth component of the vector field. You are really taking the derivative of the vector field and then taking its muth component. Okay, so in shorthand, you'll sometimes see this symbol, but this is what you really mean. Okay. Okay. Any questions here? Okay, so now we'll come to something really interesting. Okay, and we'll start seeing some connections to physics a little bit. Okay, so now we'll define the notion of parallel transport, and sorry, we've defined a notion of parallel transport, but now we'll talk about parallel transport along a curve. Okay, so we defined a curve earlier as you take an open interval from A, B, okay, and you take a map of this. So there's a parameter T which describes where I am in this interval. Okay, and I take a map C of T which gives me a point on this manifold. And so let's say at some time T, I'm at the point P. Okay, this traces out a 1D curve on this manifold. And now the coordinates of the point P in some coordinate system phi are given by some x, okay, where x is phi of P. Okay, so now imagine that there are two things that I can do. Okay, so one is, suppose I have a vector field x. Okay, this vector field x is over the entire manifold, but we're interested in the vectors of x which are at points on this curve. Okay, so these white lines, these white arrows, show the x vector field on the curve, okay, at different points on the curve. Okay, so those give me the x vectors along the curve. Now, so x is some vector field, and in components, so I can say I'm evaluating x at points along the curve. So I'm evaluating x along this curve C of t, and in coordinates, that is x mu C of t e mu, okay, evaluated on the curve. So x evaluated at points along the curve. Now we also define, okay, a vector field v, okay, and this vector field v is only defined along the curve itself. Okay, and what is v? Well, v is just tangent vectors to the curve. Okay, v are tangent vectors to the curve. So v, as we've already defined, okay, is just this notion of, I can think of it as either d by dt, or in components I can think of it as dx mu dt evaluated along the curve, okay, or evaluated on the curve times partial x mu. Okay, this is what I mean by v. So v, really, you can imagine drawing tangents to the curve, okay, tangent vectors to the curve, and v describes those tangent vectors. Okay, and v is only defined along the curve. X is defined everywhere, but we're focusing on x along the curve. Okay, so now we say that if x satisfies a property, okay, that is, if this vector field x satisfies this property, and what is the property? The property is that del v of x is 0, okay, again along the curve. for any t belonging to AB. Okay, so for n, so this remember that this is a vector. Okay, at every point I evaluate this vector on the curve. Okay, at points on the curve, and if this is 0 for all points on the curve, then we say that x is parallelly transported along the curve. Okay, we say that x is parallelly transported along the curve. So let's intuitively try to understand what that means. So roughly what we're saying is we've defined a notion of parallel transport. Okay, so I will represent vectors as parallelly transported here as if they're parallelly transported in Euclidean space. Okay, so that means usually we think of a vector like this, and if we think of a vector over here, it should look like this. If we think of a vector over here, it should look like this. These vectors are parallel to each other. Of course, we've seen that the notion of parallel on a manifold is more generally defined using using the idea of connections. Okay, but for the moment, let's just represent them like this. Okay, so these are parallel vectors. So now what we're saying is, so this is some curve. Okay, so this white line is some curve. Okay, and now the pink lines are the tangent vectors to the curve. Okay, and what we're saying is that when I take the derivative of x along the curve, the derivative of x along the curve is just 0. Okay, or another way of saying it is x is not changing as I move along the curve. Okay, x is not changing as I move along the curve. Okay, so x is not neither increasing nor decreasing. Okay, and it just stays the same. Okay, it is parallel to itself. Okay, so if such an x is, satisfies this property that its derivative along the curve is 0, okay, or the tangent vectors to the curve is 0, then you say that x is parallelly transported along the curve. Okay, so it makes sense intuitively why you define this as the notion of parallel transport. Okay, this is basically the statement that x is not changing as I move along the curve. Okay. Okay, so where again in components v is just d by dt, which I can write as dx mu dt acting on ct, and expanded in this basis of e mu's. Okay, so in components we can now write out this equation, okay, in some coordinate basis. So using this coordinate basis, I can write it as remember we had something like v mu, and then we had partial x. Okay, so this is v mu. These are the coefficients v mu. Okay, so these are the coefficients v mu, and this is just the rule that we had just worked out for what the components of the covariant derivative are, or components of the affine connection are. So it's delta x rho partial x mu plus gamma rho mu nu x nu. Okay, so these are components of the x field. Okay, again, this is evaluated on the curve. And this is expressed in some basis with coefficients rho. So I must have those basis vectors here, e rho. Okay, and this is 0. So this is a vector. Okay, so this is a vector. This is a vector. And now we can say that since this vector is 0, every coefficient of every basis vector must also be 0. So each of these coefficients is also 0. Okay, and in general, if this dx mu by dt, we'll assume it's non-zero everywhere. Okay, then and you know, in the places where it's 0 by continuity, we'll just say that that we can continue this. But this point, okay, this side, what it implies is that this expression inside the brackets, this expression which I've written here, is 0. Okay, by itself. So dx rho by dt plus this connection coefficient gamma rho nu mu nu, plus this connection coefficient times dx mu dt evaluated on the curve times x nu, this is 0. Okay, so this is an equation. What is this equation? This is an equation that components of x need to satisfy. Okay, they need to satisfy this in order for you to say that x is parallelly transported. If they don't satisfy this equation, then x is not parallelly transported. So for example, in this figure, if some of the x's, instead of being like this, let's say this was like this. Oops. This was x was like this. Then from here to here, you would say x is not parallelly transported, but from here to here or here to here or here to here, you'll say x is parallelly transported. Okay, because del Vx would be 0 at these points. Okay, but here del Vx would be non-zero. Okay, so it's not parallelly transported. Okay. Any questions? Okay, so now now we come to the notion of the idea of what is called a geodesic. Okay, so now if the tangent vector vt, okay, so if you have this curve and you have these tangents, you ask the question, is the tangent vector vt itself, is that parallelly transported? Okay, so that is, what does it mean to parallelly transport? That is, if I take this vector v and I parallelly transport it to this point, okay, so our naive intuition would be, it would be like this, okay, in the usual sense of parallel transport that we're familiar with in Euclidean space, we would say it's like this. But the tangent vector here is different from this vector, and so you would say it's not parallelly transported because it doesn't come back, the change in the vector is non-zero, okay, this is the change in the vector. So in other words, if the derivative of v along the v direction is 0, then you would say v is parallelly transported. Okay, if v is parallelly transported. If it's non-zero, then you'd say v is not parallelly transported. Okay, if v is parallelly transported, okay, then the curve c of t is called a geodesic. Okay, so with this picture, you can imagine what needs to happen for this curve for v to be parallelly transported. If this is a tangent vector here, and I move from this point along the v direction to the point q, if I move along the v direction to the point q, and then this curve, and then the tangent vector v is here after parallel transport, then you would say v is parallel to itself. Okay, and sorry. Okay, let me just redraw this. If I draw a straight line, okay, the tangent vectors are like this. Okay, at this point it's like this, at this point it's like this, and this point it's like this. Okay, and so if I take this vector, okay, this is v at the point P, I parallelly transport it to the point Q. Okay, and then I compare it with v, which is already here. Okay, sorry, v prime at q. I compare it with v at q. And if there is no difference between these two vectors, okay, then the derivative along v of v is 0. Okay, and then you would say that this curve is a geodesic. Okay, so geodesics are in some sense the straightest possible curve that you can have on a manifold. Okay, because they keep v parallel to itself as you move along the v direction. Okay, so as I move along the direction of the tangent vectors themselves do not are not changing. Okay, so that is basically what defines a straight the straightest possible path you can have in a manifold. Okay, as opposed to this kind of path where the tangent vectors, okay, are changing, and therefore when I parallelly transport the vector from here to here, I can see that it's not the same as the tangent vector here. Okay, and that's what tells me that there is that this is not the straightest possible path. Okay, that I'm following. So there's specific curves, okay, which are called geodesics. Okay, and these geodesics are the straightest possible curves that you can have. Okay, in flat space, we'll see that they correspond to straight lines. On on something like a sphere, we'll see that those geodesics correspond to longitudes or great circles. Okay, these are the straightest possible lines that you can have on a. Okay, so something like this. Okay, something that wraps around the circle over the largest possible with the largest possible circle. Okay, so something like the equator or any longitude, right? These are great circles. Okay, so these are the straightest possible lines that you can have. These are as opposed to something like this, okay, which is connecting 2 points. Okay, these are not straight paths, and they are basically not geodesics. Okay, even latitudes, okay, except the 0° latitude, those are not great circles, and this is not the shortest possible path between 2 points. Okay, so again, sorry, shortest and longest requires a notion of distance. Okay, so sorry, we're not talking about distance, we're just talking about straightest in the sense of once we define a notion of parallel transport. Okay, here again, we're using some intuitive notion of parallel transport. So what is that notion? Well, there is some notion of what we mean by parallel transport along a geodesic or along a sphere, right? We want to keep the vector kind of like pointing as close to itself as possible. Okay. But really, to define even such a notion of parallel transport, you have to define what the connection coefficients are. Okay. On a sphere, there's a particular choice that's picked out once we choose a metric. Once we choose a distance measure on a sphere, then a particular choice is picked out. Okay. At the moment, in general, you can choose any kind of notion of what it means for vectors to be parallel to each other. Okay, by defining connection coefficients. Okay, so this is a level of abstraction again. Okay, but we'll come to a very specific choice once we have specific metrics. Okay, so now what we can do is we can find out the equation that the components of V should satisfy. Okay, so the components of V, since V is a tangent vector, V is just dx mu dt. Okay, partial x mu. Okay, evaluated along the curve. So the coefficients or V mu, okay, are just these things, dx mu dt. Okay, so these are the coefficients. So we can plug in, okay, these coefficients dx mu dt into this equation. Okay, here capital X was the coefficient of the vector x, dx rho. Small. So this was capital X as opposed to small x. So now for capital X, we're plugging in dx dt. Okay, so x rho is dx rho dt. That's what we're plugging in here. So now we'll find the rule that these coordinates should satisfy. Okay, so that the curve V is a geodesic. Okay, and when you plug it in, so we'll plug in this x mu is dx mu dt. Okay, so that is we'll end up with this equation. Okay, so you can check this later. So what we'll get is d square x mu dt square plus gamma mu nu rho dx nu dt dx rho dt is 0. Okay, so this is called the geodesic equation. Okay, and already you can start to see that you're getting something like Newton's second law out of this. Okay, roughly speaking, we will see that this will be something like d square x mu d tau square. If we set our connection coefficients to 0, this is basically Newton's second law, the absence of forces. Okay, and so the claim will be that particles, okay, follow geodesics. Okay, and what tells us what is a geodesic? Well, once you have a metric, the metric will pick out a specific choice of connections, one connection, okay, one connection at all points on the manifold, and so that will be a unique connection. And then the geodesic equation will uniquely tell you, okay, what are the shortest possible paths between 2 points in space-time. Okay, and the shortest possible path in between 2 points in space-time, remember that I told you that you can show for free particles that they'll follow the shortest possible path in space-time. This will be true even in the presence of gravitational fields, but in the presence of gravitational fields, space-time will be curved, and therefore these coefficients, these gammas, we will see that they will necessarily be non-zero, okay, in every coordinate system. Okay, they will necessarily be non-zero. At least somewhere on the manifold, some coefficient will be non-zero somewhere on the manifold. Okay, and then if that is true, okay, then you'll see that you'll get these kind of, effectively this will be like some kind of force, and that's what we'll interpret as the gravitational force. Okay, and so this geodesic equation is very important. At the moment, our connection is a very general connection. It can be any kind of connection that you specify in the manifold. And once you specify that connection, this trajectory, okay, this describes a curve. So this x mu of t describes a curve. Okay, this is the differential equation that these coordinates x mu of t must satisfy. Okay, which tells you the path through the manifold. Okay, it tells you a path on the manifold, a curve on the manifold. Okay, and this is the path that it must satisfy for a path which is the straightest possible path. Okay, the straightest possible path satisfies this equation, which is called a geodesic equation. Okay, so I'll just tell you two tensor operations, and then which we'll need for next time, and then we'll end. Okay, so there are two operations on tensors. We kind of might have used them implicitly, but let me just explicitly spell out what these are. So one is what is called index contraction. So if you have a tensor which is of the form, so a tensor of which belongs to the tensor space QR, so a tensor of type QR, it takes Q vectors as inputs and it takes R dual vectors as inputs. It takes Q dual vectors as inputs. Okay, I forget how we defined it, but it takes Q dual vectors as inputs and R vectors as inputs. Okay, so it's a map from the space of dual vectors times dual vectors times dual vectors, Q times, and the space of R vectors. Okay, and what it does is it maps it to, what does it map it to?
R.
Real numbers, good. So it takes in these dual vectors and just maps it to a number. That's what a tensor is. Okay. In some specific basis, we can write the tensor with these coefficients, mu1 through mu q, nu1 through nu r. It is basically q basis vectors and r dual vectors. Okay, q vectors will take in q dual vectors, r vectors will take in r dual vectors. Okay, and the net result will be a number. Now we'll define an operation on such a tensor. Okay, and the operation on this tensor will take the tensor of type QR and reduce it to type Q minus 1 R minus 1. Okay, and this operation is called a contraction. Okay, and the contraction is very easy to understand. You take the ith index over here and you take the jth index over here. And you, instead of this vector acting on some abstract dual vector which you are yet to feed it, you insist that this ith vector acts on this jth dual vector. Okay, so you feed this jth dual vector to the ith vector. So the tensor eats part of itself. Okay, so you contract. So now you take the ith position here, the jth position here. Okay, and what you do is you sum those indices. Okay, because this ith object acting on the jth object would be like partial x mu I, okay, acting on dxj. Okay, and it would essentially take an inner product of those two, which would be result in a delta mu I delta nu j. Okay, so when the mu I is equal to nu j, okay, this will give you 1. So now I'm setting, so this will be true for every value when mu I is equal to nu j. So I'll choose mu I equal to lambda, nu j equal to lambda. Okay, so at the jth position I set this to lambda, at the ith position I set this to lambda. And now I get rid of my partial x mu I. Okay, so this only has q minus 1 terms now. And this product has only r minus 1 terms, where I got rid of the dx nu j. Okay, so now this is a tensor of type q minus 1, r minus 1. Okay, so this is called a contracted tensor. Okay, so you can reduce the rank of this tensor by taking contractions. So contractions take us from a tensor which belongs to the space of TQRM, smooth tensors of type QR on the manifold, to smooth tensors of type Q minus 1, R minus 1 on the manifold. Okay. And the second operation, this is the last line, so is you take a tensor of type QR on the manifold and you take another tensor of type q prime r prime on the manifold, then you can define the tensor product of these two tensors, which gives me a tensor of type q plus q prime r plus r prime. Okay, we've been using this implicitly, but for example, if I take the tensor product of a vector and a dual vector, okay, this is a tensor of type 1, 0. This is a tensor of type 0, 1. Okay, and now if I take the tensor product of these two, okay, this will give me v mu w lambda partial x mu dx lambda in some basis. Okay, and this is basically a tensor of type 1, 1. Okay, so this is what we mean by a tensor product. Okay, and now I can feed this a dual vector and I can feed this a vector, and then the action on that will result in a real number. Okay, so this is some tensor of type 1, 1. Okay, so these are two operations which are useful when we talk about tensors. And next time what we'll do is we'll talk about the rules for parallelly transporting a tensor. Okay, what is the rule for parallelly transporting a tensor as opposed to just a vector? Okay, and we'll define the notion of derivatives, these covariant derivatives of tensors. Okay, we'll stop. Any questions?
Sir, I had a question from last class, metric spaces.
Sure.
Sir, for example, in Minkowski space, if one were to define the metric on purely mathematical basis, then there'll be many possible 0-2 tensor fields which satisfy the properties, right? So the only thing that like isolates the Minkowski metric, the diagonal metric minus 1, 1, 1, 1, is the physical significance, like because it gives us the proper physical laws which we were looking for. So for example, if we now move to 4D pseudo-Riemannian spacetime, how would we isolate the metric which we are looking for? So I did not exactly get.
So Minkowski spacetime is a specific example of a pseudo-Riemannian manifold. Okay, so what we'll see is in general. So our entire discussion is very general here. Okay, so what we're saying is that. Okay, so let me just tell you what the rules for gravity will be. So we'll say that spacetime is a manifold. Okay, actually we'll discuss this only after the midterm, but spacetime is a manifold. Okay, and on this manifold has no metric. Okay, but once you have matter / energy, okay, this matter or energy sources curvature. Okay, the curvature is defined in terms of some derivatives of the metric. Okay, actually, to be more specific, it's defined using these covariant derivatives of the metric. Okay, and so these derivatives of the metric is proportional to this some stress energy tensor. Okay, which is roughly like the energy density of the system or the matter density. So you're sourcing the curvature of spacetime, which is related to derivatives of the metric. Okay, from some energy density. Now you have to given some t mu, you have to solve this equation to find out what the metric is. Okay, so you have to solve this equation for the metric. Okay, so once you solve for this metric, the solution is now your manifold with a metric. Okay, and once you have a manifold with a metric, okay, that basically on that manifold with a metric, now particles follow, basically geodesics, which are the straightest possible paths in space-time. Okay, so even if the space-time is curved, like imagine that it was some kind of sphere which has curvature, okay, then particles will follow these straight lines, except these are straight lines not in space but in space-time. Okay, so we have to define a notion of straight lines in space-time. Okay, now it turns out that if you solve Einstein's equations, that is these equations, in the absence of any matter or energy, that is in vacuum, okay, if you solve this in vacuum, then the solution that you get for G is in some coordinate system, you will get this solution, okay, which is eta. Okay, so basically special relativity or the Minkowski metric is a specific solution in general relativity. It's the solution when there is no matter field to source gravity. Okay, and why does it work? Well, because to a good approximation, all the gravitational fields around us are relatively weak. We'll see what it means for a gravitational field to be weak. But in the limit that they are weak, okay, you're essentially solving for this gravitational, this equation, okay, for in the absence of any source of gravity, and what you end up getting is just the Minkowski metric. Okay, so the Minkowski metric is one specific outcome. Okay, for there can be many other outcomes for what the metric is in a general spacetime.
Sir, in this whole discussion, when you're talking about particles, you mean basically particles falling freely in whatever gravitational field exists?
Yeah. So freely falling particles, which are basically particles which are not acted on by any other forces except what we would call the force of gravity. Okay, and the way we interpret the force of gravity is it's straight lines of particles follow straight lines in this curved spacetime. Okay, so they're really just freely falling inertial particles. Devashish, did this answer your question?
Yes, sir, somewhat. Yes, sir. Like, so basically, like if we were to study this as a purely mathematical theory, then it wouldn't work. Like would not be able to isolate G mu. So, like a physical.
Yeah, there's no
yeah.
reason why eta is a specific good choice on the metric of the metric, right? Other choices of metrics also work on R4.
Yeah, got it. Yes, so that was my question.
But I will say one thing, that the other assumption that we do make in general relativity is the metric has this signature, that it has 1 minus sign and 3 plus signs. Okay, so we assume that the metric, remember we talked about how many minus signs and plus signs it has. So we assume that it has 1 minus sign and 3 plus signs. Okay, and this or vice versa. Okay, it doesn't really matter as long as so this is the same as 1 plus sign and 3 minus signs. It doesn't really matter. Okay, this choice is important. Okay, this choice is something that you are assuming that your manifold. We don't know what the metric is till we solve for it. But whatever the metric is, we also assume that it has this signature. Okay, that's another assumption. That's part of the assumptions of general relativity. Okay, and that signature is basically essentially tells you that there's only one time direction. Or time-like direction.
Okay, sir. So, like, instead of working of like talking about it like an assumption, we could just say that it gives us the non-gravitational limit because we already know that STR works perfectly. Right. We could find out G mu nu without this constraint, and then
no, you still this is not sufficient to tell you what G mu nu is. What this is saying is the eigenvalues of G have 1 minus sign and 3 plus signs, but G itself doesn't have to be this 1 minus 1 1 1 1.
Yes, sir. So that is what I'm saying. So even if we work without the knowledge of the signs, we can still, like, even if G is some general function of the coordinates, we can say that for the limit that the maybe we zoom into a smaller area such that gravitational effects are negligible, we should get the flat space limit.
Yes, that's a very good point. In fact, we'll see that. So if you zoom into a small enough region, you can always find a coordinate system at a specific point. You can always find a coordinate system where G will take this form. Okay, It's always possible because you can go to the coordinate system where G is diagonal and rescale your coordinates, and G will take exactly this form. But you can only ensure this at a point. You can't even ensure this in a neighborhood of that point. Okay, if there's curvature, at some point in the neighborhood of this point also G will not be flat. I mean, G will not take this form. Okay, so what we're saying is that it's locally Minkowski, spacetime is locally Minkowski by specifying the signature. By locally we mean at a point. Okay, we can't guarantee that even in the neighborhood of a point that this will be that the metric will continue to take this form in your coordinate system. So indeed, yes, this is this local Minkowski at a point. This is imposed by our assumption of the signature of the metric, and this is too related with what we physically observe.
Sir.
Yeah, go ahead, Tosha.
Sir, how is it possible just to get that -1 1 1 1 just by rescaling? Like we can get to we can choose some basis so that it is, let's say, minus a b c d, 1 negative and 3, but where a b c d are different numbers. So how just by rescaling the coordinates we can get -1 1 1 1?
Well, that's easy to see, right? I mean, if I if I write out what the metric tensor is, it's, let's say, minus a dx0 dx0, right? Plus b dx1 dx1. Sorry, this is G, right? It's a tensor. It's a 0 to tensor. So I'm writing it in a basis, right? And now all I can do is if I rescale my basis vectors, or equivalently I rescale my dual basis vectors, I can rescale dx0 to square root a times dx0. Right? I can always change my basis vectors, right? And the way I can do this, right, is by changing partial x0. I want to preserve this inner product. Okay, so let me call this dx0 prime. So I want to preserve the inner product of dx0 dx0. I want to preserve this. Okay, and the way I can preserve this with this change is that I can write this as square root a dx0 prime, and I can write this as 1 by root a dx0 prime. Sorry, dx0. Okay, so effectively what I'm doing now is if I take this to be my vector along the x direction, I have really just rescaled my x0 coordinate by an amount square root a times x0. Okay. And if I rescale it like this, then basically this will become, in the new coordinate system, it will become -1 times dx0 prime wedge dx0 prime. Okay, and similarly you can do it for the other coordinates.
Yes, sir. Similarly for dx1 it will be root b.
Yeah. I mean, essentially, this is a distance measure, right? So it's telling you, as we've discussed, if you feed it an infinitesimal vector, where this is an infinitesimal quantity, partial x mu. So now I'll get a distance measure, which is like this, g mu nu dx mu dx nu. So essentially what we're doing is now we're feeding it a distance measure, and it's telling us what is the distance. So if I take, let's say, x0 only, right, and I take g0 0, this tells me the distance as I move from one point with x0 and some other x's to x0 plus dx and some other x's, plus dx0 and some other x's. This is telling me the distance that I travel. So obviously, if I rescale my dx0 to absorb, 1 power of square root g0 0 here and 1 power of square root g0 0 here, okay, or if I rescale my x0 itself, my infinitesimal amount. So instead of basically, this is like saying that instead of measuring in units of, let's say dx0 is not 1 unit, okay, but dx0 is now. So if just g00 is, let's say, 100, Okay, then what we're saying is that this, I mean, it's basically telling us what our unit distance is. Okay, so G00 is just a rescaling that you can do of your reference distance.
Okay, sir.
Yeah, so for the actual physics, we'll still wait a bit, okay, till probably after the midsems, where it'll probably be after 2-3 classes after the midsem, where we'll start really connecting the mathematics that we've developed for manifolds and try to connect it to the physics of general relativity.
So would you be giving us any, like, so the syllabus for the midsem includes everything up to
up to the next class. Yeah.
Okay. So will we have any like problem sheets or something for?
Yeah, I'll try to give you a problem sheet either tomorrow or day after. Okay, and it'll be practice problems, very similar to kind of questions that I'll ask you in the midsem. And most of it will be very simple, just to make sure that you're familiar with the idea of all the mathematical concepts that we discussed. I mean, at least this part, right? Not the part about regular observers, but at least this part will be to ensure that you understand what you mean by coordinate systems. Right now, a lot of this discussion was an abstraction. We'll try to apply it to different manifolds and try to understand what we mean by vector space located in different coordinates and so on.
Okay, so do we have to like submit this assignment for grading and all?
Yeah, but the deadline for the assignment will be after the midsem, not before.
Okay. Okay.
Okay, but you can use it for practice for the midsem.
Okay, sir.
Okay, any other questions? All right, if not, let's stop here and let's meet on Thursday. Okay, see you all. Good night.
Thank you, sir.
Bye.